One of the lovely things about John Saxon's books is that he mixes up his topics and gives you, the student, plenty of variety in the work that you're doing. And I love that about these books. After lesson 69 and lesson 68, with those heavy-hitting, strong algebra topics, we're going to take a break and just go off in a completely different tangent in lesson 70. And the tangent that we're going to go off on is called probability. Probability is a branch of statistics, which is a branch of mathematics, that probability has to do with how likely it is that certain things are going to happen. And it's fun because it involves lots of little scenarios that I think are fun to try and imagine. So let's just dive in and see what sense we can make of this as we go. Let's look at example 70.1. This lesson has lots of words in the book. Ugh, that's so boring to me. I hate the words. So I like to go straight to the problems and kind of explain it as we go. A fair coin is tossed 3 times and it comes up heads every time. What is the probability that on the next toss it will come up heads? Okay, let me break this down for you. By a fair coin, they mean a regular coin, a penny, a nickel, a dime, or a quarter, that is not rigged in any way. I don't know if you guys have heard of this, but sometimes in gambling halls or whatever, they will use coins that are kind of weighted so that they will always come up heads or be more likely to come up heads. So a fair coin means it's just a regular normal coin. It's not rigged in any way. Now, you guys all know that when we flip a coin, there's only 2 things that can happen. It can either come up heads or it could come up tails. Now, if you're a teenage boy, you might argue with me that I can flip a coin and make it like land on its edge. Well, you know, maybe. But chances are that when a normal person flips a coin, they could flip it 100 million times and it would come up heads or tails, but it probably wouldn't do much else. So we're assuming that there are only 2 things that can happen. It can come up heads or it can come up tails. What is the probability that on the next toss it will come up heads? Well, whenever we're figuring out probabilities, this is the little formula that we use. We calculate the number of what I like to call desired outcomes. How many times are we going to get what we want in this little scenario? And we put that in a fraction where the denominator is the number of possible outcomes, okay? This is what probability, this is how you calculate the probability of something. So we want to know how many times it'll come up heads. Or we want to know what's the probability that it will come up heads. Well, how many desired outcomes are there in this scenario? Only 1. Because it's only 1. We want it to come up heads. What are the number of possible outcomes? Well, we just said that when you flip a coin, there are 2 outcomes, heads or tails. So I'm just making this super obvious, standing up to make sure my paper is not out of the range of my camera. Okay, so the probability that when we flip a coin that we'll get heads is 1 out of 2. Okay? We just calculated it. Now let me just unpack something else that is in this problem that is meant to trick you. A fair coin is tossed 3 times and it comes up heads every time. What is the probability that the next toss will come up heads? Now let me ask you a question. If you flip a coin 18 times in a row, does that change what's going to happen on the 19th time? No. Flipping a coin is what we call an independent event, meaning that every time you flip it, it's just like it were the very first time. It doesn't matter if you got heads 18 times in a row. That doesn't mean you're more likely to get heads the next time. It doesn't mean you're less likely. Every single time you flip it, the probability is exactly 1 out of 2 that you will get heads. So that is the answer to this question, and it's meant to remind you that when you have an independent event, you don't have to take past events into consideration at all. Each flip of the coin is completely unique and different. So that is the answer. That is the probability for for problem 70.1. Let's try 70.2. This one's got a long story to it, so read along. I'm on page 285. 6 green marbles and 8 red marbles are placed in an urn. Oh my gosh, I love these marbles in the urn problem. 1 marble is drawn and then dropped back into the urn. Then a second marble is drawn and dropped back into the urn. Both marbles were red. If another marble is drawn, what is the probability that it will be red? All right, first let's draw a picture of the urn. Urns are kind of like big vasey things, right? I'm going to draw a big one. Here's my urn. And inside of it, I've got a bunch of marbles. And I wish I had my markers right here because I would use the proper colors. But there are 6 green marbles, so I'm going to make 6 G's to represent those marbles. If you've got markers or colored pencils available to you, go ahead and color them in little circles. That's what I would be doing. I would be making little green circles if I could. And 8 red marbles, so I'm going to make 8 R's to represent the 8 red marbles, okay? And my urn is magical so that they can kind of float on their own sides. Oh, here, I need to make the top of this there, so it looks like it's got an opening. All right, so we've dropped all our marbles in here. And they go through this big long thing in the problem of saying that we take one out and we look at it and then we put one back. We take one out, we look at it, and then we put one back. Okay, that is, they're trying to trick you into thinking that that matters. As long as we're putting all the marbles back, then every single time we draw a marble, we're dealing with an independent event. And what we've done in the past doesn't matter at all. So it doesn't matter that they've been drawing marbles out and looking at them, because the time that we're talking about is completely independent of all those other times. If another marble is drawn, what is the probability that it will be red? So the probability that we're going to get a red marble, notice my little nifty notation, equals the number of desired outcomes. Okay, how many red marbles do I have? 1, 2, 3, 4, 5, 6, 7, 8. There are 8 different marbles that I could draw that would give us exactly what we want, right? Because we're looking for red marbles. And we have 8, so that means the number of desired outcomes is 8. The number of total outcomes is equal to the total number of marbles in the jar, or urn, excuse me. It's not a jar. I'd like urn. We could grab any one of these marbles, and we don't know whether they would be red or green. But there's a total of, let's see, it's 6 plus 8, so that's 14 marbles in all that we could be drawing from. Does that make sense? It's pretty straightforward. So that is the probability of getting a red one, 8 out of 14. And then we can simplify this fraction by dividing both sides by 2. Since they're both even numbers, we reduce our probabilities. And that's 4 out of 7. So the probability of drawing a red marble out of our lovely urn is 4 out of 7. Cool? Cool. Now let's look at 70.3. A single die is rolled 6 times. Okay, so you guys know what a die looks like. It's one dice, and it's got the dots on it. There's a 1, and there's a 2, and here's a 3. Oh, 3 goes in. 3 goes in a row, so pretend those are in a row. Okay? It's rolled 3 times. The results are, oh gosh, now I have to strain my eyes. The results are 1, 4, and 5. No, 1, 4, and 3 in that order, right? So we got a 1 and a 4 and a 3 in that order. What is the probability that the next roll will produce a number greater than 2? Okay, so we're looking for the probability that the number will be greater than 2. Now, once again, John Saxon's trying to trick you. Does it matter that we've rolled the dice and rolled the die and gotten these scores? No, it doesn't, because once again, we're dealing with an independent event. Every time you roll the die, it makes no difference what the last person got. If you're playing a board game and the last person rolled a 6, does that mean you're going to roll a 6? No, absolutely not. Every single person's roll is an independent event. So it doesn't matter to us that it's been rolled these times in the past. We don't care. All we want to know is what is the likelihood that we're going to get a number greater than 2. All right? So we go back to our formula here. What are the number of desired outcomes? Well, let's see. Greater than 2, we could get a 3, or we could get a 4, or we could get a 5, or we could get a 6. Any one of those rolls would give us our desired outcome of a number greater than 2. So those are 4 different numbers that we could choose from. And what are the total number of possible outcomes when you roll a die? You can get a 1, or a 2, or a 3, or a 4, or a 5, or a 6. So that's 6 different numbers that you might get. 4 of them would meet our qualification here. So the probability of getting a number greater than 2 on a roll of the dice is 4 over 6, which can be reduced to 2 over 3, and there's your answer. Beautiful, right? Cool. All right. These are kind of fun, don't you think? I like the little scenarios. I like the little games that we're playing. And so now let's try. Oh gosh, we've got a couple more things to cover in this. 70.4 is kind of tricky because this time we're rolling 2 dice. And they want to know what's the probability that the sum of the numbers rolled is 7 or a number greater than 8. Now, if we're rolling 2 dice, we can get a lot of different things, can't we? So we're going to draw a little chart to help make sense of this. This is what we have to do if we're rolling 2 dice. Because on the first die, we could get a 1, or a 2, or a 3, or a 4, or a 5, or a 6, right? But also, on the second die, we can get, now I have to make all the columns, just a second. We have the same situation up here on the second die. We could get a 1, or a 2, or a 3, or a 4, or a 5, or a 6. And as you guys know from playing board games, that you add the die together to find your total roll. So our total rolls would be, I'm going to kind of make these lines darker. Okay, so then we can fill in with what we would get, what our total score would be. My pen's dying. I'm going to persevere through this lesson though. So we can just simply fill in this chart. 3 plus 1. See, I'm just filling in with all the additions. So you guys go ahead and fill this in, what your total score would be if you rolled each number on the 2 die that you're playing with. Okay, so go ahead and fill that chart in. Pause me if you need to until we get, those are all the possible outcomes you can get if you're playing. I just think of it as playing a board game and you've got 2 die. I'm pretty sure like Monopoly uses 2 die. So those are all the different combinations of scores that you might get. The question is, A, what is the probability that the sum of the numbers rolled would be 7? So I write, what is the probability of 7? Well, what we can do is we can go through and count up how many different times you might get 7. And I see a bunch of 7s here right in a line. So I'm just going to count them. 1, 2, 3, 4, 5, 6. There are 6 of them. There are 6 of our, going back to my other page, we're doing desired outcomes over possible outcomes. The desired outcome is a 7. And there are 6 different rolls that will give me a 7. 1, 2, 3, 4, 5, 6. And we're going to put that over the top of the number of possible outcomes, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. You could have done that a lot quicker if you just multiplied, but I did it the long way so you'd see exactly what I meant. So the probability of rolling a 7 can be reduced to 1 out of 6. All right? So that's how we calculate that one. The second part asks us to calculate what is the possibility that we'll get a number greater than 8. So once again, I'm going to use this little symbol to remind myself of what we're trying to find. What's the probability that we'll get a roll greater than 8? Well, I'm going to go back to my chart and I'm going to look for rolls greater than 8. This time I'm going to circle them. So I see some 9s here, and I see some 10s, and I see a couple 11s and a 12. Okay, those are all rolls greater than 8. Now I'm going to count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 possible outcomes that would meet our standard here, our qualification. So there are 10 possible outcomes, and the total number of outcomes, again, we know is 36. There are 36 different numbers you can get when you roll the dice. So let's divide both of these by 2, because I can see they're both even numbers. We simplify. 5 over 18 is our answer for the second one. Cool, yeah? Yes, I like it. It's fun. All right, now we're going to look at the next example where things get a little bit more interesting. 70.5. And in this one, we've got a fair coin, and we're tossing it 4 times. What is the probability that the first 2 times it comes up heads and the last 2 times it comes up tails? Okay, so this time, if you look in the book on page 286, there's a really cool picture. I'll try and produce it for you. So the first time you flip the coin, you can get either heads or tails, right? The second time you flip the coin, if you got heads the first time, you might get heads the second time. If you threw it heads the first time, you might get tails the second time, right? If you got tails the first time, you could get heads the second time, or you could get tails the second time. All of those things are equally likely to happen. So we can see that by the end of the second time, oh wait, I'm talking about, my picture doesn't take everything into consideration. Let me just finish explaining this and then we'll go back to our example. So what we do is we multiply the probability of each flip by the number of times that we flip. So if we flip twice, let's say we wanted to know the number of times that we could roll heads and then heads, the probability of heads then heads, the first time we threw it, we would have a 1 in 2 chance of getting heads. The second time we threw it, again, we would have a 1 in 2 chance of getting heads. It's always the same. So if you multiply them together, we find that we have a 1 in 4 probability of throwing heads and then heads, which was what our situation was. So when we have multiple events, we multiply the probability of each one. Now let me go back to example 70.5. Okay, and let's look at our scenario. A fair coin was tossed 4 times. So what is the probability that it comes up heads and heads and tails and tails? So we have, just to help you see it, we have 4 flips. And we're wondering, what is the likelihood that we'll get heads, then tails, then tails? Okay? So, what is the probability on the first flip that we'll get heads? Well, we already know with coins, it's 1 out of 2. What is the probability on the second flip that we'll get heads? Well, it's always 1 out of 2. Coins don't change. The third flip, they want us to get tails. And the fourth flip, they want us to get tails again. Okay? Every single one of those flips, we have a 1 out of 2 chance of getting that. Now, what is the chance that we're going to get it exactly like this? In order to find that, we multiply those 1 out of 2, those 4 fractions by each other, and we get, yeah, you can see, 1 on the top. 2 times 2 is 8. That's 1 out of 16. So that is the probability of getting, this is how I'm going to write it, heads, then tails, then tails. Make sense? The probability of getting that specific row of flips is 1 out of 16. One more problem, and I'm going to do this one with you because these are, each one's a little bit different and they are kind of tough. Once you get to the homework, you can go back into the explanations that we're going through now, the examples, and you can find the one that matches to your scenario, and I think you'll find it much easier. We've got a spinner. What games have spinners? Hi-Ho Cherry-O does. I don't know if you guys played that. I sure did. So now we have a spinner game, and I'm copying the little picture that's in the book. Looks like this, and then there's the little, there's the little arrow thingy that spins around. I like drawing the pictures. Okay. So we've got this little spinner. It's spun 2 times. What's the probability that the spinner stops on 4 and then on 3? Okay, so here are the spins. It helps me a lot to kind of diagram these problems out. We've got 2 spins, and they want to know what's the likelihood that we get a 4 on the first time and a 3 on the second time. Well, so on the first time we want a 4, so that's only one possible outcome. And there are 1, 2, 3, 4 different numbers to choose from. So we have a 1 in 4 probability of getting a 4 on the first turn. And then on the second turn, we want to get a 3. So what's the likelihood of getting a 3? Well, there's only one way we want that to end, but there are 4 different choices. So it's a 1 in 4 chance with each spin that we'll get one of those specific numbers. So to find out the odds of getting a 4 and then a 3, we multiply them. Oh, and look, it's the same number. So the probability of spinning a 4 and then a 3 is 1 out of 16. Yay! This is a lot, and it boggles the mind at first, but once you work through the homework and practice doing each one of these styles of problems again, I think you will find them kind of fun and cute to do. So, good luck with those, and I will see you for lesson 71.